speaker is Dustin Hite from NIST, and he's going to talk about absorbate-coverage-dependent work function patches on gold.
That's a quirky title there, but anyway, it sums it all up. So yeah, really I'm going to talk about anomalous heating from electric field noise to surfaces. Sorry. Right there. That's probably good.
Yeah.
That's okay. You think it's?
It may rub against the microphone.
Oh, I'll take it off if it does. So, and a lot of work's been done on anomalous heating over the last 20 years, where some of the results make sense, and some of them don't make any sense at all. And so, what we do is we try to study the surfaces to understand those ones that don't make sense. And the way we do it is we have a surface science system with an ion trap built into it, or connected with it. And what we do is we can move samples to over the ion to position them within 50 microns of the ion, to try to use the ion as a surface science tool. And what we're looking at here is just Kelvin probe force microscopy images. Well, they're histograms of the image. And what it gives you is how the patches are distributed on the surface. And this is from an actual ion trap that started off dirty with 2.3 monolayers of carbonaceous coverage. And then it was incrementally removed by ion bombardment to see what happens. And something pretty interesting happens here. And you might think when it gets really broad like that, that it might be noisier. Because if something's causing that coverage to change, it causes the work function to change. And if the work function changes, you can get electric field noise above the surface. And so that's why it's interesting to look at, or to use Kelvin probe force microscopy at ion trap surfaces. Or model systems for that matter, and we'll talk about that a little bit too, where we deposit carbon on a gold crystal, and it allows us to compare and contrast those things. So, I needed to thank the opportunity to participate in this workshop. I meant to say that first. So thank you very much. Yeah, so my name's up there, but I'm not the only one that participates in this project, so I like to start off with those guys first. This is my group here, where we have a graduate student. Kyle McKay is the guy that operates the lasers in the ion trap, and Dave Pappas is our group leader. And this is a collaboration between the ion storage group, and these are some of the people that are in that group, or used to be in that group, that have worked on this project. We also collaborate with Hussein and Hussein here, and you'll hear Hussein's talk right after mine. And Shlomi Kotler has been a great help. He's in a different group. And then I mentioned Christian Arrington at Sandia, because they're the ones that make our traps. We have microfabricated stylus ion traps with a very high aspect ratio to the electrodes, and they're made with X-ray photolithography, so that you can get the electrodes away from the surface. And we do side view imaging, because we're going to put a sample near the ion from the top. All right. So like I was saying, a lot of work's been done on anomalous heating, and the factors that play a role are the temperature of the electrodes. If you lower the temperature, you can get 2 orders of magnitude less heating. If you elevate the temperature, you can get higher heating rates. And but a lot of the work was just done by going from room temperature and then all the way down to some base temperature. But and these are the ones, and maybe I missed one or something like that, but these are the ones that dealt with reducing the temperature, and this one down here is the one that I'll show some data from that was for the elevated temperature trap. And so, and that's why they're in bold there. But you see, a lot of people have done a lot of work. This paper by Cheverini was a very detailed reduction, variable temperature going down to 4 Kelvin. And this paper here was very detailed work going from room temperature up to, well, we'll see. I'll show you on the graph here just one second. So the Cheverini group started here at room temperature and reduced it and got a curve that looked like that. This is linear graph here. And what I'm plotting is, and this may not be fair because I want to compare these two traps, the one that went down in temperature and the one that went up, but they're using different ions, they're using different frequencies, they're using different distances, so this isn't fair, okay? But I thought I could do it anyway, just to make my point. So this is normalized to the room temperature one, okay? And so the temperatures go down, normalized to the room temperature one. And if you take Hardman's data and put it on there, you see, and normalize it in the same way so that they sort of fit together. This curve that it makes looks really familiar. Well, to surface scientists that like to study surface diffusion, it looks like an Arrhenius curve, and I can fit that, and it fits pretty well. So it sort of hints at the fact that there's some movement on the surface that's activated, thermally driven or otherwise. And but if you look at that temperature, that's way too low for surface diffusion. So that hints at the fact that there must be some other mechanism other than temperature that's causing whatever it is that's being driven on the surface. And my story is that causes the work function to change and therefore gives rise to electric field noise. Okay? And there are those two references there. Now, the stuff that does make sense is the distance dependence, because people have done very detailed distance dependence now. First, there was Chris's group did the needle trap, where they were able to, change the distance from the electrode by mechanically moving two needles, or maybe just one. I think there were mechanisms on both sides. And they also reduced the heating rate by going to 150 Kelvin. But they got a 1 over d to the 4th roughly scaling. I think it's 1 over d to the 3.8 or something like that. But it's close enough. 2006. And then Bolden at the Wunderlich group made a trap where they could change the height of the ion above by having a variable RF on their electrodes. And they got pretty much the same thing. Let's just call it 1 over d to the 4th. And then John Cheverini's group also did it recently by making a trap where you have different traps on the same chip, but because of the shape of the electrodes, the ion height is different at different places on the chip. So in this work, you have to assume that the heating rate or the electric field noise source is the same everywhere on the trap, which we know is not the case. But whatever. If you assume that, then you can make this graph, and they get 1 over d to the 4th, and when they cool it down, they get their reduction in heating and get the same number. So that all makes sense. We had a trap where we put surfaces next to the ion, And when you brought the sample, here, this is the ion trap here in my finger, the ion's between my hand and my finger. When you bring down the surface, it pushes the ion closer and closer to the trap surface, like it's a ground plane that's coming down. And we did 4 different samples, and I'll show you what those samples are in a minute. But I'll tell you first, they were all different. But we got the same thing. So this point is the bare trap. And then we said, well, maybe the trap's just too loud, and we need to clean it again. So that's these points here. We went back and did it again, didn't see anything. Really confusing. Because these 4 samples were completely different in their surface condition. And we know that if you have a dirty trap, it is louder than if you have a clean trap. Because you can clean it and get 2 orders of magnitude difference by not even doing very much to the surface.
What's the 2 lines difference here? I didn't understand.
This one, what's the question? Are they the same slope, or why are they different?
Well, one makes it just 2 different.
We had this trap here, and then we cleaned it to try to reduce the background. And then we redid the experiment with the really nice sample and the really nasty sample. And they both heated the same. Does that make sense? Okay.
So it's not temperature, it's just cleaning.
Cleaning from here to here. It was already clean, okay? When we first put the trap in, it's up there. You know, and then we cleaned it. And then it actually, over months, it actually rises up a little bit. So we cleaned it again just to try to get it better. So that's from accumulation of stuff from the vacuum sticking to the surface.
So one of the in the clean line, one of the samples was clean and one was not.
Yeah, I'll show you the Auger spectroscopy. We do X-ray photoelectron spectroscopy now. This just shows the example of how when you bring the sample in, which is that big thing on the top that's 1 millimeter across, close to the trap electrodes, which are these things that you see here, and the ion sitting in there. When you reduce this, you reduce this. And so you're always closer to the trap. You see, until you get here, but you don't want, that's too close. I mean, it's really hard to do that. That's just the dotted lines of simulation. And the red lines are data taken from using the camera and counting pixels and things like that. Anyway, I just wanted to show you how you get closer to the trap. Now the samples look like this. There was
Sorry. When you get close to the trap, are you also changing the curvatures, right? The frequencies?
Yeah,
Don't you get then also different sensitivity to different noise spectra?
well, we always did it at the same frequency.
The same RF?
Yeah,
frequency,
you have
but
to
the
change the RF power a little bit.
Ah, okay. So you kept the secular frequency. The
Yes.
same. Ah, sorry.
Yeah. No, sorry I should have said that. But these are Auger spectra. So Auger electron spectroscopy tells you what's on the surface and how much you got. So if that black and red peak of carbon right there are really big, you can take ratios and that you can actually tell how much you got on there. This one right here is a gold crystal that accumulated a little bit after having been cleaned. And this one was just straight up cleaned electroplated gold. The one on the top was an actual ion trap because we couldn't figure out what's the difference between an ion trap and a piece of metal, right? Well, there's gaps and there's edges, you know, things like that. But it was grounded. It wasn't wired up as an RF trap. And it was really dirty. But we got it just as close. And so those colors correspond to the colors in the graph. I'll re-show it here with the heating rates. So this result was really confusing. So then we said, well, what is the difference between an active ion trap and a grounded ion trap that it wouldn't heat? And
I'm not familiar with this. If we clean out, then that OJA's spectroscopy shouldn't be very clean. What do you mean by dirty and clean out?
dirty and clean. I mean, if there's a carbon peak on the gold, okay, so all these samples are gold. They're all gold. And you can see the gold peaks here. If you have a big carbon peak, it's dirty.
But you said you clean out, right?
You clean it out.
So the only one sample clean out?
No, the trap
Well,
is
these
clean.
these two should be.
Dustin, the trap is clean, not the sample.
Well, this sample's clean.
Well, the two curves you showed was a cleaner and a less clean trap. And I think that's what the question is about.
I was totally confused. So sample is sample, just...
The green ones are clean.
Yep. Samples are the same. Trap is cleaned and not cleaned in these two sets of points, right?
Oh, the black points?
Well, any of them. It's with a clean trap.
The green one's clean.
And a less clean trap.
That's why there are two curves.
Correct. Yeah.
But the green sample is clean.
Yes.
And so it should be on this line, but these black ones here should be up here,
The point is
if it worked.
the green sample is as clean on one curve as it is on the other.
Yes.
All right.
Yeah. Because we can clean our samples. I mean, we can do whatever we want because we move them around within the vacuum chamber. And they never come out into the air unless you take it out. Yeah.
How deep does the electrode surface? So in other words, could it be that, I don't know, nanometer below the gold, you have some carbon deposits?
Yeah, but I don't know if the ion stays that far down. Yeah, I don't know. But yeah, it's like a nanometer.
Yeah. So yeah, I assume you have like really like a crystallized surface. So the idea is that you have a relatively smooth surface and that you really can think about layers. Because
That's an idealization, yeah. I mean, you've got, on the crystal, you've got terraces and steps. And there's nothing dirty down below that layer. Because I wouldn't see a clean layer when I clean it. I'd still see dirt. So I think that sort of answers it. So we tried to think about what's the difference between an ion trap that's grounded and an ion trap that has or is operational. And I could only think of one thing, that the RF was playing a role. And remember, we saw that in that Arrhenius curve, that temperature was so low, it was as if temperature wasn't enough to cause surface diffusion. It's as if the RF fields or currents or something like that are driving the adsorbates on the surface to move around faster than they would normally. So we did, and we made some new chips. Oh, those samples, these samples here were like poorly RF grounded. There was a really high inductance to get out of the chamber to the feed through. And I think that the impedance of these samples was poorly matched to the RF drive of the trap, that the trap couldn't drive it on the samples. I mean, that's what I think, but it's not proven. And it's not easy to prove either. So we made some different samples. One's a serpentine chip, and one's an interdigitated chip with coax line going out to SMAs, so that we could have a better impedance match to the RF frequency. And there were 6 micron gaps and 6 micron lines, so that if we applied RF to them, the field from applying RF wouldn't make it all the way to the ion, yet the anomalous heating would, because it's a long-range patch field. So when we did that, this is one of those samples, you see that you don't get that single power law anymore. And in fact, what you get is, I call it a double power law, but it's the sum of two power laws, the one from the trap and the one from our sample. So this curving data is an indication that we are possibly measuring heating from both surfaces now, because we fixed that RF problem. Okay? Yeah, so this is just the sum of two power laws, this green one. And if you believe that this trap had the same dependence, you can subtract them out and see if the numbers make sense. So this is just assuming that we have the same distance dependence in the trap that I showed you before, where the samples weren't heating. And then this would be the data that you get heating from the sample. These are his distances. We know those because we measure them. Maybe not very well, but and then and his heating is an order of magnitude higher than the clean trap. So that makes sense. But we just rebuilt our system so that we can go back to doing samples where we can transfer in and out. And we wired it like this. So shortly we should be able to do a real experiment that we're supposed to do to better prove this is actually coming from the sample and the trap.
So just to clarify, so typically your sample is affected further away from the ion, and because you
That's this.
treated the trap,
This is the distance dependence you're talking about? And yes, because we treated the trap, it would have a lower heating rate on this graph right here. And that's, we're assuming that we know this distance dependence, and we don't, just because the trap might have a little bit different geometry and stuff like that. And notice that it's not d to the 4, it's d to the 3.1, and that was probably because of geometry, the geometry of the trap not being planar. And by the way, this does come out being d to the 4, which makes sense because that sample was a planar geometry. Just saying. I don't know why those lines are curvy on there. That's funny. Okay. So then, another thing that doesn't make sense is when you incrementally clean the trap and measure a heating rate after removing some of the stuff for 5 minutes at a time, measure heating rate, hit it again, measure heating rate. So the coverage is going down incrementally. The heating rate goes, this is where we started. It goes through the roof and then down to, there's your low heating rate, which is like 7 or something, corner per second. And we have magnesium 25, and our trap is like 6, well, you saw what the distances were, but if there's no sample there, the ion height's about 60 microns. If you measure the frequency scaling, while you do that, you get this. And so this is kind of what we've always seen here, this 1.5 and the noise. Okay, not heating rate, but in the noise. And then something happens right around here where it just drops to, it's going to 0, it looks like, or something. I'm just showing you this stuff. I can't explain it yet. And then, another weird thing about the measurements that we have is that if you do the heating rate versus the mode frequency, and this is for both modes, okay, so sorry, I should have labeled that better. The dots are for one of the radials and the Squares are for the other radial mode that are parallel to the surface of the trap. So this is what we got before, and that's like that 1.5 in the noise. And then we heated, we hit it, removed it. I'm not showing all the data because it's a funny looking graph, but the frequency scaling went up on this graph, right? Well, it got shallower, and then on the second to last treatment, you got an asymmetry, you got an asymmetric heating. The heating in this direction is different than the heating in that direction. Yep. Oh, shoot. I'm not even halfway through. So,
Which direction was the ion beam?
It was in this direction. I have a figure of it, but I don't have it in this talk. Yeah, it was along that direction. So what we do is we try to do surface science. We've got STM, we've got low energy electron diffraction to look for order. We do XPS to tell us how much carbon is on there. And by looking at the energy, the little tiny energy shifts of the carbon peak, you can tell whether it's just carbon or hydrocarbon or whatever, something like that. And then this whole thing is hooked up into this system. There's our trap. And here's the sample that came from these tools, all in the same vacuum chamber. So it's pretty sweet. And we can look at the work functions on the surface with the Kelvin probe force microscope, and do an experiment where we deposit carbon on a gold crystal. That's our model system. And so those black points were just measured randomly. Like, it wasn't me removing it. I could deposit it on one day, I could deposit this point, and the next day I could deposit this point. And then the red ones are those data I showed you earlier where I was removing carbon from an ion trap. And this point right here is where it started. And you see it's quite different than just carbon on gold. But as soon as I hit it once, it just starts to look like carbon on gold. So it's like if you sputter it, you modify the layer to make it look just like carbon. Anyway, yeah, I mean, and then here's the carbon binding energy. Here's where it started on the trap. Where's the button? Oh, here's where it started on the trap. Looks like a hydrocarbon because it's not down here. I don't know which hydrocarbon it is. I tried to leak in air into my vacuum chamber, and there's a whole lot of hydrocarbons in air, if you didn't know that. And then it starts to look like the model system after that. All right, let's try to go through this. And the Kelvin force probe microscopy looks like this. For the ion trap electrode, you got these patches of different work functions. For the model system, deposited carbon on gold, and where's the coverage? 1.3 monolayers. They're both the same coverage. They look completely different, right? Because this is a polycrystalline, electroplated gold ion trap with large patches. You see the histogram of that image, and his histogram is here, and I've reproduced them here. And the fact that this is wide would mean that you have a lot of work function possibilities on your surface. But what we need now is for some mechanism, like an RF current or something like that, to push around this crap and change the coverage. Because if you can change the coverage, then you're changing the work function. And you can have work functions changing all over the surface because things move around. When am I done? Now?
30 minutes.
I got 30 minutes?
No.
Oh, you're saying I'm at 30 minutes. And here's the comparison of those histograms. This is the model system. You see how narrow they are? It's the work function and the coverage. And this is the ion trap electrode that was the carbon was being removed. And you see right there, that's the same coverage where the heating rate shot up before it came down. And so what I'm trying to think about is how the width of this makes the surface noisier when things are being driven to move around. And so I made a simple model, and this is my last slide. I made a simple model where I compare the data that I showed you earlier, where the heating rate went up before it comes down, with this. I guess I should write it out down here what this really is. This, the first term, 1 minus e to the minus x, is a shape like that, right? And I'm saying that that's the coverage dependence, right? So if you have no coverage, you don't have any heating. But if you get enough coverage, it doesn't care anymore. You know, the ion doesn't care if you make the crap thicker and thicker and thicker. So that's the shape for the coverage dependence. And then I just multiplied it by the width of those histograms, saying that the width of that histogram provides a greater density of states to have different coverage that would give you different work functions. And I got something that looked sort of like that. Yeah, I mean, you could do better than I did here. Like if you actually took the whole histogram into consideration when you calculate that number instead of just the width. And the width doesn't make sense on those multi-peaked ones. Which width are you talking about? So it's a little bit of a hand waving, but it sort of worked. And so I guess I won't really summarize because my colleague Hussein is going to give a talk that describes more of the atomic scale version of this to try to explain how things moving on the surface could cause noise. Okay? All right, thanks.
There were stories some years ago that everything also depends on the thickness of gold layers on the surface of the traps. What was the thickness of your gold layers?
They were microfabricated surface electrode traps that were 10 microns thick.
Okay, 10 microns.
Yeah, and the thinner ones, I don't think they heated any worse, did they?
Did you go down really much thinner? Let's say.
No, they were. It's before I joined the group. They were making them thinner. They were making them with evaporated gold, and they wanted to get further away from the dielectric substrate. So I've only been working with 10 microns, and then our stylus trap is 200 microns. Are there more?
So how would you make ion traps with a narrower distribution of work functions?
Make them out of single crystals.
Single gold crystals?
Wouldn't that be the best?
Hey. How would you do that though?
We're thinking about it. Dance Electric found a paper where people were electroplating and getting single crystals. They just played tricks with their electroplate solution and voltages and things like that. And they supposedly were growing single crystals. But then you need to clean it because everything's dirty until you clean it. But gold is good because once you clean it in the vacuum chamber, it stays clean for months. It's really good. But sputtering a crystal sort of requires annealing it too, so that you can smoothen that surface back out. And we don't know if morphology is playing a role yet. We've got a lot of experiments yet. don't want to go over too much. Here, use this one, huh? Yeah, and then there's a pointer.